Let's look at the question. Smallest string with swaps. We are given a string S and an array of pair of indices in the string pairs, where the pairs at I is an array contain A and B, indicates that two indices of the string, and the indices are zero indexed. You can swap the characters at any pair of indices in the given pair of any number of times, and after we using the swaps, we should return the lexicographically smallest string that S can be changed to. We have a string of lowercase English letters and some pairs of the form A and B, where A and B are indices in the string, and our goal is to find the lexicographically smallest string by swapping the characters the indices A and B, and there's no restriction on the max number of swaps. The important point to note here is that if we have the pairs like AB and BC, then we can swap characters at the indices A and C. Although we don't have the pairs A and C, we can still swap them by first swapping them with the characters at the index B. Thus, because we can swap the characters at these indices any number of times, we can rearrange the characters A, B, C into any order. This problem can be depicted as a graph problem, and each index is a vertex, and each given pair is an edge between the vertices. So an edge implies that we can travel from one vertex to another. In other words, we can swap them. So we have some pairs, and we draw an edge between the two vertices for each pair. So if a pair of vertices exist on the same path, then we can swap them just by repeatedly swiping with other vertices in the path between them. This demonstrates how we can swap any pair of vertices present in the same connected components. So there's no pair 0 and 7, right? But we can still swap the characters by first we swap the characters at 2 and 7, and then we swap the characters at 3 and 7, and then we swap the characters at 0 and 7. So we are done. Thus, we can rearrange the characters such that any character is at any index within the connected component. So consider the pairs of connected nodes in the graph. Once we find a connected component of indices, we can sort the characters within component to obtain the lexicographically smallest string. The reason why we sort the characters within each connected component is that it guarantees that all possible permutations of characters within component have been considered, since all of the indices are in a connected component that can be swapped with each other any number of times. So it makes sense for us to sort the characters within component so that we can obtain the lexicographically smallest strings. Sorting the characters within each connected component doesn't change the relative positions of characters within a component, but it does change the relative positions of the characters between the different connected components. Let's say we have a connected component of indices containing the characters C, B, and A, and we have another connected component containing the characters E, F, and D. And after sorting the characters within each component, the first component will become ABC, and the second one will become DEF. Thus, we can concatenate them into get the string ABCDEF, which will be the lexicographically smallest string, and after we use this swap, the S can be changed to this. So, how could we find the lexicographically smallest string? We need to sort the characters that correspond to these indices in ascending order, and then place them with I's characters at I's index. Therefore, we can break down the solution down into 4 steps. The first step, we try to build a graph by using the given pairs, and second, we find the connected components in the graph, and third, in each connected component, we sort the characters in ascending orders, and fourth, we just build the smallest string. The biggest challenge in solving this problem was trying to figure out that with infinite swaps, we can arrange all characters that belong to the same connected components in the sorted order, right? So with that hurdle behind us, our next challenge is how do we find out which indices belongs to the same connected component? If we try to find out which indices belong to the same connected component, we can use a lot of algorithms on the graph like depth-first search, breadth-first search, and union find, which are commonly used to find the connected components.